we're going to play with one of our data sets today, the HERS LDL data, and wrap up our coverage of regression. Next week we'll start talking about correlated data. So what happens when the IID assumptions of our models are not appropriate. If we have, say, paired data, pre and post measurements on each individual, then we will have correlation between those measurements on the same individual. If we have time course data, which we'll spend a decent amount of time talking about, the repeated measurements on the same individual over time are correlated. There's a new HERS LDL script that I uploaded this morning. It's all the way at the bottom in the scripts folder. So let me get that, and let me get our regression notes real quick. Okay. So, we have learned how to fit regression models, how to interpret them, and how to do inference with them. We know how, for example, to test whether a single coefficient equals a particular value. A common choice for that particular value would be 0. Is beta 1 equal to 0? That asks, is there or not a linear relationship between whatever covariate goes with beta 1 and the response? But then we also saw two more general methods of inference testing called likelihood ratio tests and F-tests. So these can be used to test null hypotheses that involve more than one coefficient at a time. Likelihood ratio and F. Both of them proceed in a similar way. Namely, we fit two models. We fit the original unrestricted model that we started with. This is the model we think is appropriate. And then also fit the model that is true if the null hypothesis is true. So we fit an unrestricted and a restricted model. And once we have done that, we can easily do a likelihood ratio test and an F-test. Likelihood ratio, you need to evaluate the normal based likelihood. Plug in your data with your fitted values from the model into the normal density and product up all the densities. Or what we've done is sum the log density values. It's equivalent. Once you have fit those two models, you can just get the residuals from them. I'm calling them E here. So there's an E1 for the unrestricted model and an E0 for the restricted model. Once you have the residuals, you can sum up their squares, and then you put those sums of squares, residual sums of squares together in this way, and you have an F statistic. Likelihood ratio you compare to a chi-square. And then Wednesday, we talked about confidence intervals. Suppose you want a confidence interval for one of the coefficients, like beta 1. Then you can construct it in a usual way. Estimate the parameter of interest, then go out plus or minus this many, some critical value from the t-distribution, that many standard deviations of the estimate. Confidence intervals, we've seen it before when we did bootstrap and simulation-based inference. confidence intervals are driven by sampling distributions. So we need a sampling distribution for beta hat, beta 1 hat, say. What this expression is saying, because we're using a t critical value here, or cutoff, it's saying that beta hat itself is approximately t. So this comes from analytical results that we expect for the sampling distribution of the betas. We also saw that if we wanted a confidence interval for some linear combination of the betas, like beta 1 minus beta 4 or something like that, we can do that in the same way, estimate the parameter that you're trying to do inference on, and go out plus or minus an appropriate number of standard deviations of that estimate. I'm going to show you an example of what this looks like today. If we do that linear combination thing, V transpose beta hat, then the estimate is easy to get. If you want a confidence interval for, say, beta 1 minus beta 4, then your estimate, V transpose beta hat, would be beta 1 hat minus beta 4 hat, the estimate. And then we need this standard deviation. What's the standard deviation of beta 1 hat minus beta 4 hat? And for that, we can make use of our general expressions for the variance-covariance matrix of the betas. In particular, the variance of a constant vector dot product with the random vector beta hat is, we've seen this before, can pull those constants out, but they get pulled out to make like a sandwich form where they're on both sides. And then in the middle is the variance-covariance of beta hat, which we know how to estimate. Let's go see an example. I'm going to get the HERS LDL data. And in our, let's see, we've got it set up right. So I'm going to just load in the data and take a peek. Remember, these are 2,800 postmenopausal women with existing coronary heart disease. They're in a clinical trial, and the purpose of the clinical trial is to investigate the effect of hormone replacement therapy. Some of them are in the control group, some of them are in the treatment group. Let's take a peek at the data. Let me change the font size here so we can see better. Okay. I need to fix the console to show up. I guess that's fine. All right, so our variables, the first one is hormone therapy, HT. That's treatment or control. Then we have age and things about several categorical variables about race and smoking and drinking and exercise. Okay. So let's do the processing that we've done before, which is to get rid of some of the variables. Some of them have lots of NAs. And some of the variables also have empty values for some of them, like drink any should be no or yes for every individual, but there's two people for whom it was not NA, it was just completely empty. And that happened for a couple of other categorical variables as well, like globe rate and So over here in the script, I have replace any empties with NA. And then what comes after that, this is new as of today, is for each of like drink any, as far as R is concerned, drink any is a factor with 3 levels. There's no, there's yes, and there's empty. And even after I replace the empties with NA, R still thinks of drink any as a factor with 3 levels. I don't want it to be treated that way, so I'm going to force it to be redefined. If I take a factor like data $drink any, and I say as.character, then it unfactors it. It's not a factor anymore. It's just a character string with NAs and nos and yeses in it. So then if I redefine it as a factor, then it will only recognize the 2 non-NA levels, yes and no. So I'm going to run this, a little bit of pre-processing, and then I'm going to drop anybody who has an NA, so we don't have to worry about it. Now let's go down to the new stuff. After correspondence analysis, I have a few regression models. First off, let's do regression, treating BMI as the response variable. That's probably not the main focus of this study to look at BMI, but that's one thing we could do. Let's model BMI in terms of a bunch of the variables. Linear model, linear regression. I have a continuous, at least numeric response variable, and I'm going to use all of these predictor variables in the model. I don't have any interactions. I haven't explored interactions. Ideally, you would, but we're just going to fit this model for now with only main effects, no interactions. I'm also mean centering age. Remember that an intercept is defined as the mean response when all the covariates are equal to 0. So if I don't mean center age, beta 0 is not interpretable. It's the mean BMI for people in the placebo group who are 0 years old. When we mean center, beta 0 has a meaning. It would be the mean BMI for those with 0 for everything, and in particular, average age. Age underscore C equal to 0 corresponds to an average aged person. Here is our model. Looks like that. Those are our estimates and standard deviations and p-values. The biggest factors a way to quickly isolate the biggest contributors would be to look at the t-statistics, the standardized coefficients, estimate divided by standard deviation. In terms of modeling BMI, smoking, yes or no, has a very strong effect. So does exercise, or lack of it, and so does age, and more than anything else, WHR, which is weight-height ratio. That makes sense because BMI should be very closely related to weight-height ratio. They should be highly correlated with each other. I included some code to investigate the assumptions of the model. We generally do that by looking at the residuals of the model. So EE is now the residuals, and we might investigate whether the data look reasonably normal. I could make a histogram of the residuals. Those don't look perfectly normal. The distribution looks skewed, right skewed, a little bit. Could also do QQ plots. here's QQ plots, or a QQ plot for the residuals. Where did the console go? I could look at QQ plots. That's not a great QQ plot. Almost every QQ plot will look pretty linear in the middle. It's really the tails that speak to normality most of the time, or lack of it. So here's a QQ plot that does not follow the straight line. The tails pull off of the line. So that's concerning. Any inference that we do that makes explicit use of a normal assumption is then suspect. Having said that, we do have a big sample size. So roughly 2,000 people, or 2,800 people almost, 2,700. That's a big sample size, even though we have a lot of covariates. So with a large sample size, I don't care all that much about that normality assumption. The p-values will be approximately right, even if the data are not normal, if you have a large sample size. Central limit theorem kind of results apply. All of these coefficients are maximum likelihood estimators, and MLEs are approximately normal with a large sample size, regardless of whether the population is normal. So I'm not very concerned.
What's the threshold where you can kind of don't worry about normality?
The question was, what's the threshold for when you don't need to worry about it? There's not a perfect answer. In the univariate case, if you just have a single, say, mean vector, or mean that you want to estimate in a population, you collect a sample of size n, and you're going to do inference about the mean. Your Stats 101 textbooks would say a rule of thumb for how big n needs to be before you can not worry about it is 30. That's a common rule of thumb. That's not a perfect rule of thumb. It depends on how skewed the population is, for example. If it's really, really skewed, you need more and more. So I don't have a perfect answer, but if 30 is the rule of thumb for univariate, then 3,000 is most likely going to be fine. One thing that I'll say, though, is if we had a sample size of 3,000, but we had 2,800 variables in the model, then we arguably don't have a big sample size. Big sample size is with respect to how many parameters do you have to estimate.
An unrelated question though. So in the beginning, you do this linear regression for like all these possible parameters in the table. So some of them are obviously more correlated with the EMI than others. So if you only consider the ones that are correlated with EMI, is it going to affect normality of the data?
Okay, question was, we've got a lot of variables in the model. Some of them will be more correlated than others with the response. And then you asked if we were to limit attention to only those that are highly correlated, would that affect normality? I don't know any reason why that would affect normality. We don't have any reason to believe that normality or lack of normality will be affected more by variables that are important to the model than those that aren't. So I wouldn't think in terms of variable selection as a means to work on the distributional assumptions. So let me see. State it again, please. Yeah. Or do you adjust? Okay, question was, when we do a regression model like this that has multiple covariates in it, we have p-values over here. Do we need to do any adjustment for multiple testing? Generally, you would not. In a context like this, you would treat each of those coefficients as a separate question, essentially. Is there a statin effect? Yes or no? I could look at the p-value. Is there an HDL effect? I could look at its p-value. The multiple testing stuff is most relevant when you have multiple tests that are all trying to answer the same question. You can think of each of these separate p-values as an answer to a specific question. The p-value for HT placebo is the p-value for is there a treatment effect, adjusted for everything else. So long story short, you don't have to do multiple testing adjustment when you have a regression model and p-values for every coefficient. Multiple testing, you want to worry about that when you're using multiple types of assessments to try to estimate one question. Like in the pollution data, if we had 3 or 4 different pollution variables in here, we could look at each one and say the p-value for hydrocarbons is this, and the p-value for silicon dioxide is that. But and that's not a problem without doing any adjustments to the p-values, it's okay. But if our question instead was, is there any pollution effect on mortality, say, we could answer that in multiple ways. We could ask, what about hydrocarbons? Is there an effect of hydrocarbons? Is there an effect of silicon dioxide? What if I consider both of them together? What if I consider all of them and take them out simultaneously? Every one of those potentially could be pointed at as my answer to the question of is there a pollution effect is such and such. So if you do 5 tests and you're going to say yes to your research hypothesis, if any one of those 5 tests come up statistically significant, that's where the problem is. If you do more than one test to assess a single null hypothesis or a single research question, then you are accumulating chances of errors. In this case, I would not do any. If it was the pollution data and I was interested in is there a pollution effect, then it would be sensible, I think, to test whether there's an hydrocarbon effect and test whether there's a silicon dioxide effect and whether there's a nitrous oxide effect, and maybe some combinations of those, and do Bonferroni adjustment on that collection of p-values. So think of it like for every scientific question that you have in mind to answer with your data, ideally there's one test, one p-value. If there's not, then you would think about doing multiple testing adjustment. I have a meeting at 1:30, so I'm going to have to leave at 1:15, just FYI. So let me show you a couple of things. First, what we might most be interested in with this model, given the context of the experiment, it's a clinical trial looking into is there an effect of hormone replacement therapy. The most interesting entry here would then be the treatment entry. Beta 1 is a coefficient for yes or no, did you get treatment? So looking at this row, we have a p-value that's large, and we would say, accounting for all these other things, once all these other things have been accounted for, there is not a statistically significant effect of treatment. What does it mean to say adjusting for these other things? When we put covariates into a model alongside some variable of interest, what we're essentially doing is assessing the treatment effect within groups that are similar on all those covariates. If you had enough data in all these different categories, what the coefficient estimate for placebo would be is go estimate the placebo to treatment difference in those with this age and this non-white status, smoking status, everything else. Then go estimate the coefficient among a different collection that's defined by your covariates. If you could estimate beta 1 for every combination of your covariates, then beta 1 hat would end up being a weighted average of all of those. Beta 1 hat is a mean difference comparing placebo to treatment, and we interpret it as among people who have the same values of everything else. That's sensible because that guards against confounding kinds of things, where maybe there is a difference in mean BMI comparing hormone replacement therapy to placebo, but maybe it's just because everybody in the hormone replacement group was old and everybody in the placebo group was young. That type of thing is referred to as confounding because you get maybe a misleading picture if you don't do this adjustment for other variables. So ideally, when you're planning a study and building a regression model, you want all the relevant variables in here. We'll talk a little bit more about that strategy because it's not trivial. When you have a data set in mind, you're going to do an experiment. There's lots of variables you could collect. There's always tons of variables that could be collected. You don't want a model that has lots of unnecessary variables in it because that will actually detract from your statistical power. But you want to make sure you have the relevant ones in there to guard against confounding kinds of things. So there's a little bit of an art to building a model. We'll talk more about it this semester. Before I run out of time, let me just show you the code I have in here. I have a couple of examples. One is a confidence interval for a linear combination of the betas. What I'm doing specifically is, let's compute a 95% confidence interval for the mean response for an individual with a specified set of characteristics. Specifically, I want confidence interval for mean BMI for a person who received the treatment, who had average age, was white, non-smoker, non-drinker, does exercise, no HTN meds, no statins, non-diabetic, and no PDM pills. Weight-height ratio is 1, glucose is 100, and so on. So I just specified a specific person that I want a confidence interval for. And we can get that using our regression model. What I just said would correspond to beta 0 plus beta 1 plus 100 times beta 2, and so on. So in order to get a confidence interval, we just need to do this. This is my collection of coefficient or covariate values that I want to compute for. The first one is for the intercept. I need beta 0. The 0 is because this person's in the treatment group, and R has parameterized that variable so that it's 0 for treatment and 1 for placebo. So I want intercept, treatment, age C is 0 because they're average age, and so on. The last few, I said DBP was equal to 75, systolic blood pressure 135, triglycerides, and so on. So if I do that, then here's my estimate. It's dot product of those coefficients with the estimated coefficients. It's going to be beta 0 hat plus 1, 2, 3, 4, 5, beta 6 plus beta 11 plus 100 beta 12, and so on. Let me run this, and then I need to wrap it up. So here's the estimate. I pulled out the estimate of the residual standard deviation. When we do summary fit in R, one of the things it spits out for us is this number here, which is the estimated sigma for the residual distribution. And we know that the variance of my linear combination is sigma squared, I'll estimate it with sigma hat squared, V transpose X inverse V. That's what I have coded up here. I'll let you look at the code some on your own, and I'll spend some more time on it Monday. But here is a confidence interval for that particular person. I also have code for a likelihood ratio test and an F test for testing whether the coefficients for those meds, there were HT meds, statins are meds, DM pills are meds. So suppose we wanted to test null hypothesis that all of those have coefficients equal to 0. All three can be simultaneously pulled out. That's where we need a likelihood ratio test or an F test. So I have code here to do likelihood ratio and then F. And I also included some code for a slightly more complex question. Suppose we wanted to ask whether the coefficients for LDL and HDL sum to 0. That's a little different. And it does not fall within the purview of likelihood ratio test and F test because it's not a nested model. So I have an example of using Bootstrap. Monday I'll show you Bootstrap for regression. It's the same idea as what we've done before, sample with replacement, but we have to sample the whole individual with replacement. Okay, I got to run. Any questions? Yes? How can we know the way that R has parameterized things with the treatment variable? The variable name was just HT. In our data set, it's just capital HT. In the output, it says HT placebo. That means R represents HT as either hormone therapy or placebo. And the fact that it says HT placebo here means this coefficient is for placebo, which means the intercept in this case is treatment. You can also tell, you know that R will treat the lowest alphanumeric level as it will order the levels by alphanumeric values. So in this case, we had placebo and hormone therapy. Hormone therapy is lower alphanumeric because H comes before P, so I would know it's going to treat that one as the intercept. Yeah. Okay? All right. Have a good weekend.